Welcome back, everybody. Today, we're going to talk about what I consider to be the most powerful tool in the area of linear feedback control system design, and that tool is known as the Root Locus. Okay, so what do we know so far? We've seen that the transient response was influenced by the location of the closed-loop poles in the complex plane. We've seen that the steady-state tracking error was influenced by the type of the transfer function we have available to us, and that is the open loop transfer function. We've seen that we can easily determine the stability of any system, including open loop or closed loop, via two ways. The first way was to look at the location of the poles in the complex plane in terms of specific locations, and also by using the routes criteria to quickly determine if we are dealing with a stable or a non-stable or maybe asymptotically stable system. But the remaining question that hasn't been answered yet is, how would those poles in the complex plane move as the gain of the open loop transfer function varies from 0 to infinity? Okay? So, because by varying that gain included in the open loop transfer function from 0 to infinity, we will see an impact on the closed loop poles, and we'll see them moving around in the complex plane, and thereby maybe for some value in terms of range for that open loop gain, maybe those poles will shift onto the right hand side of the plane, but then will come back onto the left hand side. So this is the tool that we're going to use to analyze that kind of motion of the closed loop poles in the complex plane as a function of the open loop static gain as it varies from 0 to infinity. And all this will be in section 5.7, Root Locus. So the first thing we're going to do in that section is to look at how can we construct a root locus given an open loop transfer function, and then how can we draw out or map out the location of the closed loop poles in terms of the gain values, okay, ranging from 0 to infinity. In the subsequent lecture, the next lecture, we're going to see how to use this specific tool and turn that into a design to facilitate the design of more complex control laws that go beyond the proportional derivative, proportional integral derivative controllers we've seen so far. In that case, we're going to talk about compensator. So how we're going to use the root locus to design linear compensators. And remember that the main difference between a compensator and the control laws we've seen thus far is that the compensator is a bit more complex in terms of its structure, yet the key advantage is that it will add some beneficial filtering effects. Okay, so the system is corrupted by noise coming from the sensors perhaps, and having a compensator to control the system as opposed to a very simple control law will have some key benefits. Okay, so to kick off this discussion on root locus and how does that relate to mapping the position of the closed loop poles in a complex plane as function of the open loop static gain, let's go back to our modified PEd controller for spacecraft, single axis control. Okay, so I always like to go back to a block scheme diagram that I can now translate in terms of transfer functions. So we have our simplified dynamical equation, which is our double integrator dynamical model. Looks like this. And this calculates the actual angle of the plant, or actual angle of the spacecraft, which is spinning about a single axis. Here we have the derivative component of the controller, Kd times S, like this. That would be the net torque applied to the spacecraft, control torque as opposed to perturbation torque. We also feed back the current angle of the spacecraft and compare this with what the user wants in terms of reference signal, R of S, minus the current angle to produce the error signal between the desired angle and the actual one. And this is being multiplied with the proportional gain Kp. Okay. So the first thing we'll do here is to come up with the open loop transfer function. And because we've done that a couple of times already, I remember that on top of my head, this open loop transfer function will be this over 1 over j s squared plus kds, and all this times kp. Okay? I'm going to get kp over j s squared plus minus, so plus kds. Okay? So this is my open loop transfer function. As you can see, the gain of this open loop transfer function happens to be the proportional gain. Okay? Referred generically speaking, when you talk about transfer functions, that would be equivalent to your static gain. Okay? I'm going to say gain of the open loop is your proportional gain Kp. Now, I said in the introduction of this lecture that root locus will allow us to analyze the location of the closed loop poles as a function of this particular gain here. In that case, the proportional gain of our controller. But how does that make sense? If we're starting from the open loop transfer function and we are varying the gain from 0 to infinity, well, how does that relate to location of the closed loop poles if we're using the open loop gain? I don't see the connection here. Well, let me explain that connection. That is because the closed loop transfer function is obtained, as you know, with G open loop over 1 plus G open loop would give you Kp over J s squared plus Kds plus Kp. Okay? If you look at the location of the closed loop poles here, you get it by solving the denominator equal to 0, or in other words, you get the poles by solving what's known as the characteristic equation. You would get, you would need values for J and Kd to know exactly where the poles are. So let's assume, just for the purpose of this discussion, that J is equal to Kd and both are equal to 1. If you do so, you will end up with s squared plus s plus Kp, which would give you the poles of the closed loop transfer function located at minus 1/2 plus minus square root of 1 minus 4 Kp over 2. Okay? And how does that relate to this? Well, that is because if we have a map of the closed loop poles in a complex plane, and if we were to set Kp equal to 0, because remember, the root locus is a map of the closed loop poles whenever Kp ranges from 0 to infinity. Well, whenever Kp is exactly equal to 0, you get this characteristic equation. Okay? And you would get the pole locations whenever Kp is equal to 0. Well, look at what we had for the open loop transfer function. We had the exact same characteristic equation. or the exact same denominator of the transfer function. And this is where I can say that the root locus is a map of the closed loop poles of the system, starting at the open loop poles, and that corresponds to Kp equal to 0, all the way to Kp is equal to infinity. So as soon as Kp is larger than 0, then the poles are no longer the poles of the open loop transfer function, but then become the poles of the closed loop transfer function. Because again, when you let Kp range between 0 and infinity, the poles you get at this specific value corresponds to the poles of the open loop transfer function. And this is why we initiate the construction of a root locus solely by looking at the open loop transfer function in terms of its poles, okay? Because that is the starting point of the root locus. But as Kp moves away from 0 and increases, then this value comes into play, and that will shift the location of our poles in the complex plane, but in terms of the closed loop poles now. Okay? So let's have a more detailed look at the pole locations here. And specifically, let's have a look at what would happen if Kp is equal to 0. Well, if Kp is equal to 0, what you're essentially calculating is the poles of the open loop transfer function, as I just mentioned and demonstrated by comparing G open loop with G closed loop. Okay? That'll give you poles that are at S equal minus 1/2 plus minus square root of, sorry, the square root was only applicable to the numerator here, okay? That's why I said that doesn't look right. So it'd be minus 1/2 plus minus 1/2, meaning that the poles of the open loop transfer function or the poles of the closed loop transfer function, whenever Kp is exactly equal to 0, will be given by one pole at minus 1 and the other pole at 0, at the origin of the complex plane. Okay? Now let's set Kp larger than 0. And now we're talking about the poles of the closed loop transfer function. Because as soon as Kp gets larger than 0, the poles are no longer representative of the open loop transfer function, but rather the closed loop transfer function. Where we get two poles at minus 1/2. So repeated poles at this specific location. Because 1/4 back into this generic expression for the poles of the closed loop transfer function will be minus 1/2 plus minus square root of 1 minus 1, right? 4 times 1/4 is 1, so this is 0. And you get minus 1/2 plus minus 0, and thereby you obtain two poles that are exactly at the same location. And now, whenever Kp gets larger than 1/4, these are the poles of the closed loop transfer function again, all the way to Kp equal to infinity, right? In that case, well, you get what you have here. So S will be equal to minus 1/2 plus minus square root of 4 Kp minus 1/2 times J. So a pair of complex conjugate poles in the complex plane. So as you see here, by varying the open loop gain, which was our Kp in this specific example, we have obtained different locations for our poles in the complex plane, starting from the pole locations of the open loop transfer function up to pole locations for the closed loop transfer function thereafter. So if you were to draw this on the complex plane, you not only now draw pole locations, but you want pole locations as function of Kp, so that you get essentially a map, okay? And you start at Kp equals 0, or you start at your open loop transfer function, -1 and 0. Let me draw them in a different color to better highlight the fact that those poles are really for the open loop transfer function, G open loop. G open loop, or implying that you're looking at Kp equal to 0. And then in red, I'm going to draw the pole locations for the closed loop transfer function, or any values of Kp larger than 0 and all the way to infinity. Okay? So what we've noticed here is that whenever Kp is equal to 1/4, the poles are both at -1/2. -1/2, -1/2. So they meet up there. Okay? And then whenever Kp is larger than 1/4, then the poles become complex conjugate, where the imaginary part of the poles are a direct function of Kp. So whenever Kp will increase, that will increase the imaginary part of those poles, meaning that the poles would actually move away from their initial locations obtained with the open loop transfer function, meet up in the middle at -1/2, and then you get a pole shooting right up and the other pole shooting right down, like that. So that tells you that if you have this block scheme diagram of a modified PD controller acting on a single axis spacecraft rotational motion, as you increase Kp, or as you crank Kp from 0 to infinity, that would shift the transient response of the closed loop system, because the poles will be moving, okay? So if that is the characteristic you get for the pole locations as function of Kp, you might say, boy, that doesn't suit my need, because I would really like to have my closed loop poles, say, in this area. But I know that based on the system I have, that would be impossible, because the natural behavior of the poles locations in the complex plane with the controller I have in place is giving me this. So the only allowable positions for my poles in the complex plane are the map I've drawn, right? Or the routes, the routes I have drawn here. Okay? Think of it as when I first learned that more than 15 years ago, the professor told me that you have to think about a root locus as streets with bus stops, okay? So the bus stops are the location where you can hop on the bus or drop off the bus, have to be along the streets, okay? And the bus cannot deviate from the streets. So you are really limited to those pole locations in a complex plane. But you say, oh boy, I'd really like to end up here. So the trick that we're going to see in the next lecture would be to come in and change the route for the bus, okay? Or in other words, bend the branches of our root locus, and then make sure that the bus ends up stopping at our final destination that would correspond to the desired pole locations as they were calculated based on the performance in terms of requirements from the client. Okay? So that is the key idea behind Root Locus as it applies to design, but we're going to leave that part of the design aspect for the next lecture. So today's objective will be to see how can we obtain the root locus, or the allowable positions for the poles of the system, given an open loop transfer function. Okay, and again, don't get confused, because now we have different tools in our toolbox to analyze linear feedback control systems. Some of them depend on the open loop transfer function, some depend on the closed loop transfer function, and some would rely on both. Okay, so to summarize so far, we have the steady state tracking error, which is a time domain specification. That one was related to the system type. How do we get the system type? By looking at the open loop transfer function and specifically determining how many integrators do we have in our open loop transfer function. Okay, so steady state tracking error, open loop transfer function. Routes criteria or route stability analysis, the array we have constructed last time. This is all about the closed loop transfer function, because we want to use this tool to analyze the closed loop stability of the system. So route is closed loop transfer function. Now, the root locus, you're going to need both. The majority of the work is going to be based on the open loop transfer function, but in one of the steps, we're going to need to use the closed loop transfer function. Okay? So please keep that in mind as we move forward. I'm going to say now 5.1, 7? 5.7 was root locus. Okay, root locus. And now 5.7.1 is going to be how to draw a root locus that we can use as our basis in the next lecture as a design tool. Just by looking at the root locus, we'll say, gee, the root locus don't go through the desired pole locations. I better bend those branches and make sure that the poles end up exactly where I want them to be. And for that, we'll need to add additional zeros and additional poles to the root locus that will bend and move the poles around and bend the branches in exactly the way we want. And that will lead us to talk about phase lag and phase lead compensators. Okay? But one thing at a time. So the way that we're going to obtain or draw a root locus is a very simple methodology, and in fact this is a step-by-step procedure, and there are 9 steps involved in the procedure. Okay? Step 1 is the easiest, because step 1 tells you that the root locus is symmetrical about which axis? About the real axis. That means that there's no way that you can obtain a root locus that would have one pole over here, but not its complex conjugates back down here, because that won't be symmetrical about the real axis. So if there's one pole here, it absolutely means that you have another pole down there. One here, one here. One over there, one over there. One on the real axis, fine. Fine, totally fine, because this is the axis of symmetry. So if there's one pole on the real axis, that's fine. But as soon as the pole is away from the root axis, from the real axis, it needs a counterpart onto the negative imaginary part. And same for the zeros. If there is a 0 here, you better have a 0 down there. 0 here, 0 here. 0 on the real axis, no problem. That one doesn't need to have its complex conjugate. Okay? So that's all that step 1 tells you. There's nothing to do. This is just something to remember, essentially. So that is one of the 9 steps done. Okay? Easy peasy. Now step 2. And this is where our open loop transfer function will come handy. Because that step tells us that the number of branches will be equivalent to the number of poles. Poles of what? Poles of our open loop transfer function. Okay? That's all you have to do for step number 2, figuring out the number of branches that will be part of the root locus. In the previous example, where we had the 2 poles, one at the origin, one at -1 for open loop, and they were meeting up in the middle and then shooting up and down. In that situation, we had an open loop transfer function with 2 poles. And as you saw in the root locus, we had 2 branches. One, 2 branches or 2 paths, essentially. Okay, because one pole will lead to one path along the root locus. That's all you have to remember. But the key point here is that you need to look at the open loop transfer function. Okay? Step 3. In that step, you need to determine where does the root locus start and where does it end. Start and point. Well, the starting point you already know, because the root locus will start at the poles of the open loop transfer function. Start, let me say at the poles of the open loop transfer function. This corresponds to when you have k of the open loop gain equal to 0, essentially. And where do we end? Where we end at the zeros of what? Of our open loop transfer functions. G open loop, and that will be whenever k is equal to infinity. What if you don't have any zeros for the open loop transfer function, as we had in the previous example, right? Well, in that case, it means that the poles, the poles would simply fly off to infinity along asymptotes. And in that case, we had 2 asymptotes, one straight up, one straight down, and you saw that the poles would end up flying to plus infinity and minus infinity along those 2 asymptotes. That's what we mean here. So that would be whenever there is more poles than zeros of the open loop transfer function. N means n poles, and m is for n zeros of open loop transfer function. So I'm going to say that GOL, the open loop transfer function, has n poles and m zeros. Okay? So here, number of branches was then equal to n poles. But if you have more poles than you have zeros for this transfer function, it means that there's no way that you're going to get the n poles ending up at n locations dictated by the location of the zeros, because there are more poles than zeros. So you don't have sufficient zeros to catch all the poles, if you will. In that case, you're going to get the poles that you have in excess of the zeros, quantified by n minus m. So you're going to get n minus m branches or paths in the complex plane that will go to infinity along what's known as asymptotes. Okay? Asymptotes are direction along which you have n minus m poles converging to at infinity in terms of the value of the static gain K, or Kp in the previous example. Okay? Speaking of asymptotes, we need to calculate them. Okay? And calculation of the asymptotes will be in step 4. Asymptotes. How many asymptotes do we have? Number of poles in excess of zeros. We have n minus m asymptotes, because think of asymptotes as replacement for zeros that you don't have enough to catch all the poles. But those poles you have in excess need to go somewhere, right? And that somewhere is along asymptotes. And that's why you need to have n minus m asymptotes for these additional poles that cannot be caught by the zeros in the end. So those are straight lines, okay? So here in step 4, what we want to determine is where in terms of angles are we going to draw those asymptotes. In the previous example, we had one up, one down, but you could end up in a situation where, if you look at the complex plane, real imaginary, you could have 3 asymptotes. One like that, one like this, one like that. Okay? And this is what we need to determine. So the way that we're going to measure the orientation of those asymptotes is that we're going to calculate an angle denoted by gamma, and that gamma will be equal to 1 plus 2k, where k is just an index here. That's not related to the static gain of the open loop transfer function in any way, shape, or form, over n minus m, which is the number of asymptotes, times pi, because this is an angle, right? And you do that for all k equal to 0, 1, 2, blah, 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 all the way to n minus m minus 1. So if you have 2 asymptotes, which we had in our previous example, it means we're starting off the calculation for k equals 0, but we had n minus m, which was equal to 2 because we had 2 poles, no zeros, but then minus 1. So this index variable k will then range from 0 to 1 only, because that was 2 minus 0 minus 1, which is 1. So 0 and 1, so we had 2 asymptotes to calculate. One calculated with k equals 0, and the second one calculated with k equal 1, okay? Fine. So if we had 3 poles in excess of the number of zeros, then n minus m would be equal to 3 minus 1, 2. So you'll do the calculation for k equal to 0, 1, 2 to figure out the orientation of the 3 asymptotes, okay? Now, where do you measure this orientation from, or what would be the reference? This is measured counterclockwise with respect to the real axis. Okay? So in the previous example, where we had that asymptote flying off in this direction, that one was calculated with k equals 0. So 1 minus 0, 1 times pi. So it'll be pi over, we had n minus m equal 2. That is the asymptote at pi over 2, measured counterclockwise from the real axis, okay? And when we had k equal to 1, we had 1 minus 2, so that's minus 1 pi over 2, or minus pi over 2. Okay? So minus pi over 2 is the same as 3 pi over 2. And that gave us this asymptote. Minus pi over 2. Okay? So measured counterclockwise, positive on the real axis in this direction. Nice. So far this is pretty straightforward, right? You can almost turn off your brain and just follow the steps I'm giving to you. And one step at a time, you'll be able to figure out all the pieces put together to end up with the full root locus of the system of interest. Now step 5. And note we're going to do 2 examples immediately after that to kind of put everything together. Step 5. We're going to calculate intersection of our asymptotes with the real axis. Because now we know that in our example, we had one asymptote at pi over 2, straight up, and minus pi over 2, straight down. But where do they intersect the real axis? We don't know yet. Maybe they intersect very close to the imaginary axis, or maybe they intersect the real axis further out to the left. Still at pi over 2 and minus pi over 2. But we don't know the exact location of that point along the real axis. And this is what we're going to calculate in step number 5. If you don't have any asymptotes, don't bother doing this step. Okay? But if you have n minus m asymptotes, you need to do step number 5 to figure out where do they meet or intersect the real axis of the complex plane. Now, there's a specific situation that says if there is only one asymptote, by virtue of step number 1 that told you that the root locus is always symmetrical about the real axis, if there's only one asymptote, there's no way that you could get this asymptote to be going like that, or going like this, or even like that. Because by virtue of the symmetry, that would mean that if there's one going here, you better have another one going down there. If there's one shooting straight up, you better have another one down here. And similarly for this one inclined, say at 45 degrees, there needs to be one at minus 45 degrees. But if you happen with only one pole in excess of the zeros, the only choice you have is to have your asymptote directly on the real axis, say like that, to ensure that you still satisfy step number 1. I'm going to say, in that case, you get the asymptote directly on the real axis, such that you don't need to calculate any intersection point in that case, because there would be a multitude of intersections, right? Because it lies directly onto the real axis. But if you get 2 or more asymptotes, then it means that things will be symmetrical, and you can have one asymptote flying off at a direction in the real axis, in which case you need to calculate the intersection point denoted by sigma equal to the summation of all the poles from I equal 1 to n poles minus the summation of all the zeros. How many zeros we have? We have m zeros, like that. And you're going to divide that with n minus m, or the number of asymptotes. Now for this calculation, because you're going to end up with complex conjugates and real poles and or zeros, because here you want the intersection along the real axis, this calculation only considers the real parts of the poles and zeros. Only consider the real parts of your poles and your zeros. poles and zeros of what? Of the open loop transfer function. So unless otherwise noted, everything is done from the open loop transfer function's perspective. There's only one step in the entire procedure for which you'll need to calculate the closed loop transfer function and use it. But otherwise, everything is done with the open loop transfer function. Okay, only 4 more steps to go through. Step number 6. Now in step number 6, we'd like to determine what part of the paths lie along the real axis of the complex plane. Or in other words, figuring out what part of the root locus follows along the real axis. And for this, it's not an equation, it's just from visualization of all the poles and zeros you had placed in the root locus. You need to count. So the way that we count is that we start at the origin here, and we count by moving to the left. So I'm going to say from right to left. Okay? What do you count? Well, you count everything you encounter. If that is the open loop zeros and poles you have for the open loop transfer function, you start here and you count all the zeros and poles that you encounter as you move further to the left. And whenever the summation of any poles and zeros you encounter gives you an odd number, that means that the root locus will lie on the real axis at that point. If you get an even number, you stop drawing root locus on the real axis, okay? I'm going to say odd number of, let's just call them objects for the time being. These are poles and or zeros. Odd number of objects. Drop your pen on the real axis. Whenever the net objects encountered so far up to that point gives you an even number, you raise your pen. So pen up. You stop drawing, okay? So let me do a quick example of what we have here. We're starting at the origin. We move to the left. Ooh. We have 2 poles. 2 poles is an even number. Pen is up. We encounter a third object, a 0. Pen is down. 3, 3, 3, 4, 5. This is odd. Keep going. Oh, I hit those 2 zeros. I was at 5, 6, 7. This is still odd. Keep going, keep going. Oh, I've hit an 8 object, which is then even, and pen is up. Okay? So that means that in this example, the root locus will lie on the real axis only along the red line. Okay? That's the idea behind step number 6. It is just a visualization aspect of all the poles and zeros you have in your root locus. And make sure you go from right to left to count and not the other way around. Okay, almost done already. Step number 7. In step number 7, we want to figure out the break-in and or breakaway points of the root locus along the real axis. Break-in or breakaway point is whenever you had poles moving along the real axis and they meet each other and they knock themselves out of the real axis, that will be a breakaway point. And that is what we had in the quick example we had begun with, where we had one pole here, one pole here, whenever k was equal to 0. As we were increasing k, those two poles moved towards each other, knocked themselves. One went up, the other one went down, like that. So that would be a breakaway point from the real axis because you are departing away from the real axis. There are other situations where you could get poles moving towards the real axis like that, knocking themselves up again, and one moving to the right and one moving to the left thereafter. That would be a break-in point because you're moving from away the real axis towards the real axis, and boom, at that point you stay on the real axis, so you are breaking in the real axis, whereas here you are breaking away from the real axis. But the key of step 7 is to figure out at what location along the real axis are we transitioning either from the real axis to the real axis or from the real axis to away the real axis. If that makes sense to you, okay? So we're looking for the intersection of those key points along the real axis. To figure this out, you need to look at a differential equation, s with respect of s minus b, derivative of a with respect to s, and you're going to equal that to 0. What is a, what is b? Where a is the open loop zeros, or equivalently the numerator of your open loop transfer function, and b is defined as being the open loop poles, or the denominator of the open loop transfer function. Okay? So the break-in or breakaway points always need to satisfy that differential equality relationship. Okay, so you plug AS for what it is, you plug B for what it is in that equation, calculate the derivative of B with respect to S and the derivative of A with respect to S, and then you'll be in a position to solve for the location of the break-in and breakaway points along the real axis, okay? That is the equation you're going to use. And but don't worry, we're going to do 2 examples right after that, where you'll have a chance to look at how to use that practically, okay? 2 steps remaining. Step 8. Step 8 is about figuring out the arrival or departure angles of complex conjugates poles, or zeros, okay? So step 8, we'll look at the departure angle or arrival angle of each complex conjugate poles and zeros respectively. Why respectively? Because departure angle is always from a pole and arrival angle is always at the 0. And that one is done. Okay? Good news is that if you don't have any complex conjugates in terms of open loop poles and open loop zeros, you can skip that step. So going back to our very simple example of the initial pole at the origin and at -1, all we had was two real poles, no complex poles. And therefore, we didn't have to calculate departure/arrival angle because we didn't have any complex conjugates, poles and zeros, okay? So departure angle, and you do that for all complex poles, okay, is going to be equal to pi minus the summation of all the angular contribution of the poles to that complex conjugate pole for which you are about to calculate its departure angle, plus all the angular contributions of the zeros to that specific pole, which is a complex pole for which you are calculating the departure angle of the root locus, okay? And then you need also to calculate the arrival angle for a given zero. I'm going to say for all complex zeros, you need to do that calculation, which is going to be pi minus the contribution of all the other zeros onto this specific one. Contributions, zeros to that specific one, but then add all the angular contribution of all the poles with respect to that specific zero that you are doing this calculation for. Okay? We'll see with practical numbers how we can determine the individual contribution for each other poles and of all other zeros and complex plane onto a given one. It's just trigonometry, okay? Knowing the real part, the imaginary part, how can you figure out the relative angle between one pole to, say, another zero? It's just by using trigonometry. Nothing too difficult here. Okay, and the last step is to figure out the intersection of the complex of the root locus with the imaginary axis of the complex plane. And this step can also be skipped if you know at that point that your root locus is not going to intersect the imaginary axis at all. So step 9 is going to be about intersections of complex of root locus with the imaginary axis of your complex plane. Why is that an interesting thing to calculate? Well, to get a more accurate representation of the root locus, obviously, but also in this step, we should be able to figure out for which the value of the open loop gain, Kp in our example, or generically speaking, just K, that would make the poles transition from the left-hand side to the right-hand side of the complex plane, or vice versa. Because they're going to move from right to left or left to right at these specific intersections of the root locus with the imaginary axis. And for obvious reasons, this is a key thing to consider. Or in other words, finding the limit that you can crank your open loop gain to without having the poles switch from left to right or going from asymptotically stable to unstable region, which would be a bad thing. Okay, so you want to make sure that you keep your gains in a region where all the poles remain on the left-hand side without them crossing over. And this is where, for the first time, you have to use the closed-loop transfer function. You obtain the closed-loop transfer function, and then you're going to replace all the S terms in that closed-loop transfer function with J omega. And then you're going to look at what you obtain. Because this is numerator over denominator, you can rewrite that as numerator equal to denominator. And then you're going to equate the imaginary parts of both sides of the equation you're going to get. And that would be to solve for the intersection points along the imaginary axis. If you are also interested into calculating the gain value that would make the poles to intersect the imaginary axis at those specific points, then you also need to equate the real parts on both sides of the equation. Okay? And that would be to solve for gain value at the intersection. And that's all there is. Okay? So this is really a recipe. There's not much thinking involved. Just make sure you follow the step-by-step procedure as outlined on the whiteboard today. And be cautious about what transfer function you're using for each single step. And again, you only use the closed-loop transfer function in the final step. Otherwise, everything is based on the open-loop transfer function. And I would highly recommend that you draw the root locus as you go along. Okay? Now let's do 2 numerical examples to put everything together to make sure that we know how to perform these individual steps. And ultimately using this as a way to design more advanced linear feedback compensators and apply that to spacecraft rotational motion control. Okay. Now, first example is going to be, I like to start by just giving you a block scheme diagram and let you figure out on your own the open loop transfer function out of it, as well as the closed loop transfer function. E of S multiplies the static gain K, and this goes into another transfer function that will be 1 over S times S plus 1. This calculates the output, and the output is being fed back here. So based on that, it's up to you to draw the root locus. Okay, well, I know that pretty much all the steps are based off the open loop transfer function, so let me figure it out. Open loop transfer function, in that case, it's just K that multiplies this one, or alternatively K over S times S plus 1. Now I need to figure out how many poles do I have, how many zeros, and where they are in the complex plane to begin with. I'm looking at that and I say, okay, I have 2 poles and no zeros. Where are my 2 poles? I have one at the origin and the other one at -1. Okay. This will just be the example I had given you for when we had modified KP from 0 to 1/4 and things like that. but then let's do it properly, going through all the steps, okay? So this is the basic ingredient I'm going to use to come up with the root locus. Okay, step one. Well, this is the reminder about the symmetry of the root locus. Got it. Let's move on. On step two, how many branches do we have? We have n equal 2, n equals 0, and therefore n minus m is going to give me 2 branches. Or, sorry, n branches. Like that. Where do they start? Step number 3. Well, they start at the open loop poles, so at 0 and minus 1, and they end up at the zeros. Well, we don't have any zeros, so those 2 poles will end up along asymptotes. Okay? So we're going to say that both branches start at open loop poles, i.e. at s equals 0 and at s equals minus 1, and the branches end at open loop zeros. But because we don't have any zeros, we're going to say that they end up along asymptotes. Step 4, speaking of asymptotes, how many do we have? We have n minus m asymptotes. Okay? How are they oriented with respect to the real axis? Well, let's figure out the gamma angle. Gamma 1, gamma 2. So gamma of the first asymptote, and gamma 2 for the second asymptotes. Okay? And that is your 1 minus 2k pi over n minus m. This one is calculated with k equals 0, and therefore you end up with pi over 2 for the first orientation of the first asymptote, and the orientation of the second asymptote, again 1 minus 2k pi over n minus m, but this time calculated with k equal to 1. And that gives you sorry, minus pi over 2 for the second asymptote. So let's draw what we've obtained so far. We have this real, imaginary, open loop poles. You can draw them already. One at 0, one at minus 1. I know I have 2 asymptotes. One is going to shoot straight up at pi over 2. The other one is going to shoot straight down at minus pi over 2. But I don't know where. So for the time being, let's just locate them arbitrarily on the root locus at some arbitrary intersection with the real axis. And then in the next step, we'll calculate our sigma, which will be the intersection of our asymptotes with the real axis, so that we can place them both exactly where they are. Okay? So here, n branches or 2 branches. All right. Step 5. Intersection of asymptotes. Intersection of asymptotes with the real axis. That's your sigma equation. And if you plug the numbers for we have, let's go back to the equation itself. We're summing all the poles minus all the zeros, j equal 1 to m, and the poles I equal 1 to n, divided by n over m. Okay? In our case, we don't have any zeros, so that's easy. And we're summing all the poles together by considering only the real parts. Well, it turned out they are already along the real axis, so that becomes even easier. So we have the one at 0 plus the one at minus 1 over n minus m, which is 2, which means that the intersection of both asymptotes along the real axis is going to be right here at the middle, minus 1/2. And now I can draw my two asymptotes exactly where they meet the real axis. Okay, starting to look like something. Step 6, the root locus on the real axis. I'm going to use the red marker for that. And that's where you need to count all the objects you encounter starting at the origin and moving to the left. Whenever that number of objects is equal to an odd number, you drop the pen down and you draw. And if the number becomes an even number, pen up and you stop drawing, okay? I'm starting at the origin. There's already something there, so that's 1. 1 is odd, pen down. 1, 1, 1, 1, 1. Oh, the second object, pen goes up, and I stop drawing there. Meaning that the root locus will be comprised on the real axis between those two poles. So that is step 6, root locus on the real axis. I'm going to just say C root locus on the left in red, okay? That's what I did. Step 7, break in point of the root locus along the real axis. Break in slash break away points along the real axis. Okay, because we're starting with both poles along the real axis to begin with, it means that we're going to get breakaway points because they will probably at one point move away from the real axis, all right? But if you had complex conjugate poles, maybe they would want to break in the real axis like that and do their things afterwards. But whenever you start with a pole already on the real axis and you want to figure out if that pole will break away or break in the real axis, well, obviously, it means that it's going to want to break away because it was already originally along the real axis, okay? So in that case, we're talking about breakaway points. But regardless, the equation is applicable to break away or break in. That will be AS times the partial derivative of B with respect to the S variable minus B and derivative of A with respect to S. What is my A? A was the numerator related to the zeros, okay? So without essentially this gain value K, which is static gain, which doesn't have a predefined value yet, okay? So all you're considering for A is just the S minus Z1 times S minus Z2, etc., etc. But because here we don't have anything, all we have is 1, essentially. And our B is related to our denominator, which is just going to be S times S plus 1. So back in that expression, A is 1. Derivative of B with respect to S Well, to help me out, I'm going to rewrite it as s squared plus s, such that I'm going to get times 2s plus 1 minus b, s squared plus s, partial derivative of a with respect to s. Well, it turns out that a is not even a function of s, so that becomes 0. And this needs to be equal to 0. Okay? That goes away, and I'm going to be left with 2s plus 1 equal to 0 to figure out the breakaway point, such that it is going to be at s equal minus 1/2. Now notice that here, that breakaway point corresponds to the intersection of the asymptotes with the real axis, but it doesn't need to be always like that. You could get an intersection with the real axis for the asymptotes that would be different than a breakaway point. Let me draw real quick such a situation for you. Okay? If you end up with a complex root locus with a bunch of poles and zeros all over the place, sometimes what would happen is that two poles would fly towards each other, meet up, and instead of flying up and down, they would want to fly along asymptotes that may have an intersection different than where those two poles meet on the real axis. So let's pretend that the intersection point of the asymptotes is here, away or further to the right of this pole. And that's an asymptote, another one, and obviously we need a third one. Okay, and maybe both poles would do kind of a complex maneuver like that and end up following the asymptotes, yet the breakaway point of those two poles being in between them would be different than the intersection of the asymptotes. That can very well happen. Okay, intersection of the asymptotes here, breakaway here. All right, but they can end up being the same as well. It really depends. This is a case-by-case analysis. You cannot really generalize this result. Step 8. That's where we were talking about arrival, departure, angle from poles and to zeros, okay? But here, from complex conjugate poles all the way to complex conjugate zeros, but here we don't have any complex poles and or zeros in our situation, right? All we have for the open loop transfer function are two real poles. So that equation doesn't apply. And that makes you super happy because you've just saved 5-10 minutes doing an exam. Yes. Lastly, step 9. This is to figure out the intersection of the root locus with the imaginary axis. Okay? So what you do is that you go back to your characteristic equation, which is always denominator equal to 0. But this is the characteristic equation of what? Of the open loop transfer function. But remember that step 9 deals with the closed loop transfer function. So you need to calculate the closed loop transfer function in the first place. And if you do G open loop over 1 plus G open loop, then the characteristic equation of this will give you s squared plus s plus k equal to 0. So this is the characteristic equation that you need to use in step 9. Okay? Actually, that was sub-step 1 of step 9, if you remember, obtaining this equation. Was that step 2? I don't know. One of the sub-steps within step 9. Anyway, you need to obtain the characteristic equation of your closed loop transfer function. G closed loop. And then what you do is that you replace the S variables with J omega, where you need to remember that J is the equivalent of square root of -1, such that when you end up with S squared, so the square of square root of -1 will give you -1, okay? Such that you're going to get minus omega squared for S squared in terms of J omega plus J omega plus K. And then what you do is that you equate imaginary equal to imaginary of that equation. But turns out that there is only one imaginary term in that equation. So imaginary on the left equal to no imaginary on the right. Or in other words, J omega equal to 0. And that tells you that omega is equal to 0. And therefore, the intersection of the real axis of the root locus with the imaginary axis is at S equal to 0, right here. It turns out that we already knew that from the get-go, right? Because with K equal to 0, you get the open loop poles, and one of them being directly on the imaginary axis. But that just confirms what we already knew, okay? Now, if you want to figure out what value of K you're going to meet or intersect with the imaginary axis, go back to that equation, but this time you do real parts equal to real parts. Okay? So you forget about the imaginary component of this equation, and you would end up with K equal J or equal omega squared. Right? Real equal to real, like that. So the K value at which we're going to cross the imaginary axis is going to be equal to omega squared, but we've already determined that omega was equal to 0 at that specific point, and thereby the value of K that would end up with the root locus intersecting with the imaginary axis would be K equal to 0. Surprise, surprise. We already knew that. Again, this is just to illustrate how can this step be applied, but if you already know the answer, I mean, feel free to skip the step. But don't get wrong. Don't make a mistake, okay? Because if you skip a step and you end up with a bad result, then I'm going to be knocking a couple of points off, right? It's always better to do a thorough analysis and complete all the steps, even though some of them are kind of obvious. Like here in step 9, the intersection of the root locus with the imaginary axis was obvious that we had only one point at the origin here corresponding to K equals 0, okay? Because of the location of the asymptotes. We knew already that the root locus would be looking like this. Boom, 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 they meet up. One goes up, the other one goes down. And that's the end of it, okay? Now let's do another slightly more complex example. I have a bunch of examples here, so let me just pick one which is kind of interesting. Okay, let's do that one and then we'll call it a day. This one I'm going to do a bit quicker because by now you should be familiar with all the steps and how to use the equations. For example 2, I'm giving you the following block scheme diagram where you have the open loop gain K, then goes into the transfer function, which would be 1 over S times S plus 1 times S plus 2. Most of the time, I'm going to give you the transfer function in this form already so that you can easily extract the zeros and poles of that without having to decompose a polynomial in terms of its roots and spend a lot of time on that, okay? So, first things first, G open loop, K, S, S plus 1, S plus 2, like that. I have got 3 poles, n equals 3. I've got no zeros, n equals 0. Where are my poles? Well, I've got a pole at s equals 0. I've got a pole at s minus 1. I've got another pole at s minus 2. That's what I've got. Okay, step 1. Symmetry. Easy peasy. Step 2. I've got n branches, or in my case, I've got 3 branches for my root locus. Step 3. Where do they start? Well, they all start at the open loop poles. So s equals 0, s equals minus 1, and s equals minus 2. Where do they end? My 3 branches. Well, the end points for my branches are all going to be infinity. Why? Well, because I don't have any zeros to catch any of those poles. And that tells me that I've got 1, 2, 3 asymptotes. Okay, because in step 4, n minus m asymptotes. N minus m in my case is 3 minus 0. So I've got 3 asymptotes towards which my poles will flying off at k equal infinity. Well, what about their respective direction measured counterclockwise from the real axis? Where I've got gamma 1 calculated with k equals 0. Gamma 2 calculated with k equal 1. And gamma 3, the third one calculated with k equal n minus m minus 1, that would be 2. And that's not a 6, but that is indeed a 0. So remembering the equation, we have 1 minus 2k over n minus m, 1 minus 0 over 3 gives me pi over 3, or 60 degrees. For the other one, 1 minus 2 times 1, so that's minus 1 over 3. It's plus. Is it plus or is it minus? Ooh, did I make a mistake with the equation here? It is plus. That's what I gave you, I believe, in the step-by-step procedure, but I think the way I've used it in my example was with the minus, okay? Gamma is 1 plus 2k over n minus m times pi, okay? Sorry about that, my bad. So then I'm evaluating gamma with k equal 1, 1 plus 2, 3 over 3 times pi. So that one's at pi. And the last one with 2 will give me 1 plus 4 over 3. So 5 over 3 times pi. Like that, okay? This is a plus, not a minus, as I had said in the previous example, I believe. So these are the respective orientations of my 3 asymptotes, measured again counterclockwise from the real axis. Or in terms of degrees, if you want, this is equivalent to 60 degrees, 180 degrees, and that would be 300 degrees. That's convenient because it tells me that if I go back to my root locus, and I usually start after step 4 to start laying things down. I had 1 pole at 0, 1 at minus 1, and 1 at minus 2, like that. My 3 asymptotes 60, 180, and 300 degrees, meaning that I've got one like this, one like that, and a one to the left. And that is convenient because it tells me that I am indeed symmetrical with respect to the real axis. Okay? Like that. I don't know where this point is along the real axis. I'll figure this out in this very next step, in step 5. Okay? The step 5 is all about intersection of my 3 asymptotes, in that case with the real axis. So this is my sigma, summation of all the poles minus summation of all the zeros, over n minus m. Okay, I've got 3 poles. 0, plus minus 1, so minus 1, plus minus 2, so minus 2. I've got no zeros. And this is 3, so then that will be minus 1. So those 3 asymptotes all intersect the real axis exactly at this pole here, which was at minus 1. So let me prepare them like this. Okay? Now, step 6. Let's say C, root locus. In an exam, I don't need you to explain to me what is step 6 because I already know what is step 6. I just want you to go to the little sketch of your root locus and just say refer to my root locus on the next page, for example, or you would draw the root locus ideally in a different color just to make things a little bit simpler. Okay? So starting at the imaginary axis, counting towards the left, whenever it is going to be odd, pen down, even, pen up. I'm starting, there's already 1. This is an odd number, so pen down. Boom, 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 boom. Oh, this is the second object I encounter, pen up. 2, 2, 2, 2, 2, 2, 2. Oh, third one, pen down, all the way to minus infinity. Okay? Can you see the difference in color? Yeah, not super obvious on camera. So all here was in red, and that part from the third pole all the way to minus infinity in red again. Okay? That was step 6. Making good progress. Step 7. Step 7 is breakaway, break-in point. I'm just going to say break points. I can figure out later if they are breaking away or breaking in. But just from what you see, there are probably break away points because everything is already starting on the real axis. On the real axis. So here, I need to refer to my opening transfer function to define my A. So the A is related to the numerator, where you would just write down S minus Z1 times S minus Z2, S minus Z3, all the way to S minus Zm. But because I don't have any Zs or I don't have any zeros, all I have is a gain essentially. I consider that this is simply 1. Now B of S is my denominator related to all my poles. And we had S, that was multiplying S plus 1 times S plus 2. I know for this I'm going to need to calculate dA ds, so let's do that right now, save some time. It's going to give me 0. But I'm also going to need dB, ds like that. For this, I like to multiply everything. I'm going to get s squared plus s, or multiply s plus 2 here. I'm going to get s cubed plus 2s squared plus s squared plus 2s. Okay, so this is equivalent to that when everything got multiplied together. such that the derivative of this is going to be 3s plus 3s squared 4s. Oh, they were, so 3s squared, sorry. 3s squared. So therefore 6s plus 2. Yeah, okay. And then I just applied that to my generic equation that told me that that was A times dB ds minus B times dA ds, all this equal to 0. Remember that? Turns out that my dA ds is equal to 0, so I can remove that term right from the start. So I'm ending up with this dB ds term. I was multiplying 1, or just saying that 3s squared plus 6s plus 2 is equal to 0. Now this one is not super obvious to solve by hand. So in an exam I would say, okay, for this polynomial the roots would be this and that, without telling you where you need to apply this result given from me. But here the roots of that polynomial will be s equal minus 0.423, and the other one will be s equal minus 1.577, right? Quadratic equation, or to the power 2, meaning that you're going to solve for two values of s that will make this equal to 0. Those are the two values. Again, not obvious to do by hand quickly during an exam. So I would give you the roots if you encounter something like that. Don't worry about it, okay? But then you have to be smart here and go back to the results of step number 5, where you had found that the root locus was comprised between those two poles and between the last pole and minus infinity. Because here you're getting two breakpoints. One at minus 0.4, this is 0, minus 1, minus 2. The first one is at minus 0.423, so somewhere in the middle here. Okay? But the second one, look, minus 1.5, lying between that pole and that pole. But we know that there's no root locus between those last two poles. So that breakpoint is not eligible because it doesn't lie in our root locus. Our root locus is the red part, okay, along the real axis. And here we're talking about breakpoints on the real axis. So the only possible solution is this one at minus 0.423, and that would be a situation where the breakaway point does not correspond to the intersection of the asymptotes along the real axis, okay? Cool. Step 8. Departure, arrival angles for any complex zeros and or complex poles. Look at what we have. I'm going to say not applicable because we don't have any complex poles or zeros. Step 9, intersection with the imaginary axis. And this is where you need to think and not go too quick, because you would be tempted to just reuse the characteristic equation of the open loop transfer function, yet you need to play with the closed loop transfer function here. And in that specific feedback configuration, you should know by now that closed loop is equal to open loop over 1 plus open loop. And that would give you k over s times s plus 1 times s plus 2 plus k, or alternatively k over s cubed plus 3s squared plus 2s, as we had obtained previously, but plus the numerator. That is your closed-loop transfer function, and therefore your characteristic equation that you're going to use for this step is just going to be denominator equal to 0. So characteristic equation of closed-loop transfer function, s cubed plus 3s squared plus 2s plus k equals 0. Good. Now, what do we do next? The next step, you need to replace the s variable with what they are, and that is omega j. So omega j of s cubed would be minus j omega cubed. And then with the s squared, square root of minus 1 square is just minus 1, so minus 3 omega squared. Here we're going to get plus 2 j omega plus k equal to 0. And now you have imaginary terms and real terms in that equation. Okay, this is real, the 0 is obviously real on the other side, whereas the j terms are your imaginary terms in that equation. So the trick is then to say imaginary equal to imaginary. So forget about the real terms, and you're going to get minus j omega cubed equal to minus 2j omega. Or alternatively, I'm going to keep going in black because you can probably see it better. The negative sign or negative j terms cancel out, and you're left with omega cubed equal to 2 omega. Or alternatively, to make it a little bit more obvious for the omega value that would make this relationship valid, you could just write omega that multiplies omega squared minus 2 equal to 0 by pulling this back onto the other side. And that gives you two values for omega that would satisfy this relationship. Okay, so first omega equal to 0 and omega equal plus minus square root of 2. So three values, sorry, that was a cubic relationship. One value here and two values for the omega squared terms. So 1, 2, 3 values of omega. That would be corresponding to the intersection of the root locus with the imaginary axis. Does it make sense? Let's go back. Omega equals 0 means that one intersection point would be at the origin. Hey, we knew that from the very start because we already had a pole that was intersecting with the imaginary axis. That one is a given. And now we also have omega is equal to plus minus square root of 2. Well, guess what? These correspond to those locations here. Okay? So that would be plus square root of 2 and minus square root of 2. Now, you might be also interested into figuring out at what values do we cross the imaginary axis along the asymptotes at those two specific points. Well, all you have to do is to equate the real parts of that equation. And that would be, blah, 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 blah. Look at that, minus 3 omega squared plus k equals 0. This is only the real terms in that equation, or in other words, you could say k equal to 3 omega squared. Omega is was determined to be plus minus square root of 2, without forgetting the j, obviously, right? We are along the imaginary axis. So just for completeness, don't forget the j terms there, such that well, omega is square root of 2, okay? The location is omega j, so that's why the j, you have to report them here. But for your hand calculation here, we had obtained omega equals square root of 2 plus minus and 0. So you're going to cross the imaginary axis, right? The other one was 0 at k equals 0. This is associated with omega equals 0. Okay, and that is s equal omega j, or s equals 0 times j. That corresponds to here. So whenever k is equal to 0, you get a crossing here. We knew that. The second value for k that would make the root locus to cross again the imaginary axis would be obtained with omega is equal plus minus square root of 2. And because this is square, that only gives you one value. That value is going to be 6. Because square of square root of 2 gives you 2, regardless if it is positive or negative, right? Because omega square is plus minus this, but this square. So the plus minus signs here become irrelevant, and you're left with 2. And that would be at omega equals square root of 2 plus minus, or alternatively, whenever s is equal to plus minus square root of 2j. So at those two crossing points, plus minus square root of 2j, this is whenever k is equal to 6. So as you go from k equal to 0 to k equal to 6, you get two poles that are crossing the imaginary axis. So it won't be a good idea to keep increasing your gain beyond k equals 6, because your gain will be along the positive part of the complex plane. Okay? So altogether, you could just redraw the entire root locus a little bit neater based on everything you've obtained so far. K equals 0, that's where you are. Keep increasing your gain, and you now visualize the closed loop poles as opposed to the open poles at k equals 0. What's going to happen is that because you have two asymptotes here, and that the root locus exists here and over there, it means that this one will just fly on its own towards the left. Those are going to meet up here at minus 0.423, and you would end up with those two poles knocking themselves up. At that point, one will fly towards this asymptote, the other one will fly down along the other asymptote. They would cross the imaginary axis at square root of 2j and minus square root of 2j. Okay? And that is when you visualize from k equals 0 to cranking up the gain k. Whenever k is equal to 6, I would say that this is your limit to remain in the asymptotically stable region, because at k equal to 6 exactly, you get stability or sustained oscillations. It's not stable, but it's not asymptotically stable as per past discussions. And whenever k gets larger than 6, and that means that your poles are now in the right-hand side of the complex plane, and the whole closed loop system is now totally unstable. Okay? I hope that kind of makes sense to you. It's, again, just a simple step-by-step procedure. Think of it as a recipe. You are cooking a root locus out of the main ingredient, which is your open loop transfer function, and I cannot stress that enough. If you were to begin the process of the closed loop transfer function, the whole thing would go would not make sense in the end. Okay, so start the root locus construction or cooking, because this is a recipe, from the right ingredient. And that ingredient is the open loop transfer function. Thank you so much, guys, for watching this video. Hope you're following along. I'll see you next time with the discussion on how to use this as a design tool. All right, take care. Bye.